Dr. Aida. In this video, my group member and I will present about the assignment of power system analysis. We are from group 9 and our group leader is Yap Zhi Xuan and my group member has Wong, Loong, Muhamad, Shahrul, Aiza, Subasthran, Jaythaan and me, Shahrul. The question for our assignment is this, and I will present about the question A. List out the difference in representing the power system for load flow and short circuit studies. For the first difference, we represent the power system in the form of admittance, or named as Y bus in the load flow studies, while for the short circuit studies, we represent the power system in the form of impedance, or named as Z bus. The second difference is we only analyze the original power system network in the load flow study. However, for the short circuit studies, we are required to analyze the positive sequence network, negative sequence network, as well as zero sequence network. The last difference is we do not consider the grounding impedance in the load flow studies, but we include the grounding resistance in the short circuit studies. That's all from me. Thank you. First difference, we represent the power system in the form of admittance, or named as Y bus in the load flow studies, while for the short circuit studies, we represent the power system in the form of impedance, or named as Z bus. The second difference is we only analyze the original power system network in the load flow study. However, for the short circuit studies, we are required to analyze the positive sequence network, negative sequence network, as well as zero sequence network. The last difference is we do not consider the grounding impedance in the load flow studies, but we include the grounding resistance in the short circuit studies. That's all from me. Thank you.
A very good day to my lecturer Puan Aida and my fellow friends. So my name is Yap Zhi Xuan, and today I'm going to proceed with our group 9's presentation for question B. So basically this question is about unbalanced fault, and we are required to find the unbalanced fault current for this given 4-bus power system and since all the impedance are given in per unit, so we don't have to convert them into per unit anymore. So we straight away just use the given impedance here. Okay, next. So this will be the table of conversion we are going to use when we convert the one line diagram into the zero sequence circuit We are going to have a look at this table later on. So first we are going to convert the given circuit from the question into positive sequence as well as negative sequence. So we are going to have a look at positive sequence first. So basically positive sequence is basically we just swap the components with their respective impedance For the generator 1, the impedance is J0.05, transformer 1 J0.15, transmission line impedance 0.6 J0.6 and J0.3, transmission 2 impedance is going to be 0.05 J, and generator 2 impedance is 0.05 J. Okay, since the question mentioned that the fault for this question is at bus 1, so we are going to have a look at basically we are going to calculate the exact Thevenin from bus 1 here. Okay, so we can see that the circuit on the right is in parallel with the circuit on the left. So we are going to solve the part on my right first. As we can see here, both the transmission lines are parallel. So J0.6 is going to be parallel with J0.3 plus both the impedance here, which is in series. So we are going to get a value of J0.3 ohm for the right side part of the circuit. and from the left part side of the circuit, basically it's going to be 0.05 plus 0.15 lah. It's going to be J0.2. Okay, first for the Z1 Thevenin, it's going to be J0.3, which is the right part of the circuit in parallel with J0.2, the left part of the circuit. So for Z1, we are going to obtain J0.12 ohm for positive sequence circuit. For negative sequence circuit, basically it's the same as the positive sequence circuit, but we have to remove the generator, both the generator in the circuit. So the calculation is simply the same as positive sequence, and similarly Z Thevenin for negative sequence Z2 is going to be J0.12. Okay, now we're going to see how we're going to get the zero sequence circuit for the given circuit for the question, and we're going to do it with the help of the table here, which I've shown just now. Okay, so first it's going to be a generator. So the generator impedance is J0.05, and then followed by the transformer T1. For transformer T1, it is connected from delta to Y to ground. So by referring to the table here, it's going to be at column number 3, from delta to Y to ground connected. So first, the transformer is going to get disconnected first, and then the impedance is going to be connected to the ground. So we're going to apply it into our zero sequence circuit here. First, it's going to be disconnected, and then the transformer 1 impedance is going to be connected to the ground, which is then followed by the transmission line here, as we can see, 0.6 in parallel with 0.3, we're going to get J0.2, followed by transformer number 2. Okay, for transformer number 2, the question mentioned that the transformer number 2 is connected from Y to ground and is connected to delta. Y to ground to delta. Okay, now we're going to refer to the table. Y ground to delta, and we're going to get first the transformer 2 impedance is going to get connected to the ground, and then it's going to get disconnected. Okay, so we apply it into our zero sequence circuit here. So first XT2 is going to get connected to the ground, and then it's going to get disconnected, which is then followed by generator 2 impedance J0.05, and yeah, that's it. So there's one key note here. Since the question mentioned that the circuit is bolted, this indicates that the fault impedance for the circuit is going to be 0. So for ZF, we just substitute it with 0 lah. Okay, and then same like just now, we are going to calculate Z Thevenin from bus number 1. So for this case, it's going to be J0.2 plus J0.05 in parallel with J0.15. So basically, you calculate this, and we're going to obtain J0.09375 for zero sequence circuit. Okay, so after obtaining all the impedance value for each circuit, now we just substitute the values into the formula given. So for this question now, question A, the question wants us to find the line to ground fault. So we just substitute the values we obtained just now into the formula in order to obtain the symmetrical components for current. Okay, after substituting them, we are going to get IA0. We're going to get negative J2.9963, and it's the same for both IA1 and IA2 lah. We're going to get the same current for all three of them, which is negative J2.9963, and then we just substitute all three of this value into the matrix in order to get the current for each phases IA, IB, and also IC. Okay, by solving the matrix, we are going to get IA equals to negative J8.9889, IB we're going to get 0, and IC is going to be 0 as well. So from the matrix we see just now, there's A and also A squared component. Basically it's just A, just substitute it with 1 at the phasor angle of 120 degree, while for A squared it's going to be 1 at the phasor angle of 240 degree. And for single line to ground fault, it's going to be equal to IA, which is negative J8.9889 per unit. Okay, that's it from me. Thank you.
The value of IA in the equation IB and IC comes from the value A in the above. So A is equal to 1 with the angle of 120 degree and A square is equal to 1 with the angle 240 degree. So we just substitute the value from IA0, IA1 and IA2 in the previous slide into this equation. Same goes to the value of A and A square into the equation of IA, IB and IC. So the answer for IA is equal to 0, IB is equal to negative 7.217 per unit and IC is equal to 7.217 per unit. So since the fault current in line-to-line fault is equal to IB, so fault current is equal to negative 7.217 per unit. So that's all from me.
Good morning, my name is Wong. I will present about how to find a both double line to ground fault and bus 1. First, we have the formula of phase A fault current, which is in zero sequence, positive sequence and negative sequence. First, we can find the phase A fault current in zero sequence and we get the J 3.252 per unit. Next, we can find the phase A fault current in positive sequence and we get the negative J 5.7927 per unit. And lastly, we can find the phase A fault current in negative sequence by using the formula, and is equal to J 2.5406 per unit. So next, after we find the fault current in phase A in zero sequence and positive sequence and negative sequence, we can find the fault current in phase A, phase B and phase C. So by using the formula, and then we find the fault current in phase A is equal to 0 and fault current in phase B is equal to negative 7.2169 plus J 4.87805 per unit, and we can find the fault current in phase C with this number, and then lastly we can determine the fault current, and fault current is equal to fault current in phase B plus with fault current in phase C, because fault current in phase A is equal to 0. So lastly, we can get the double line to ground fault current is equal to J 9.7561 per unit.
Last but not least, I myself Subasthran Thedsinamoothy, and I'm here today to explain the fourth part of question B. The question asks, determine the new line-to-line fault to bus 1 through a fault impedance ZF, which is J0.1 pu. Is the fault current increases or decreases from the value of 2, and justify. As they already give the ZF, which is J0.1 pu. From the given ZF, which is J0.1 per unit, we can already calculate IA node, IA1 and IA2 with the formulas as shown in these slides, and then with the values that we obtain for IA1 and IA2, which is negative J2.9412 per unit for IA1, and then for IA2 J2.9412, we can insert them in the matrix, and then in order to find IA, IB and IC. Alright, in order to find IA, IB and IC, 3 times 3 matrix has been used, which is multiplied with the IA node, IA1 and IA2, and then for IA, which is equals to 0 minus J 2.9412 plus J 2.9412, which is ended up 0, and then for IB, 0 plus 1 with the angle of 240 degree, multiplied by negative J 2.9412 plus one with the angle of 120 degree multiply with J2.9412, we will obtain negative 5.0943. And then for IC, we will be using the same formula and we will obtain 5.0943. And then from these values of current, we will get that IF is equals to IB, which is negative 5.0943 per unit. And then this is the diagram which we use to show the case. Alright, the fault current decreases. According to the question asks whether the current is increases or decreases. As a conclusion, the fault current decreases with the addition of ZF. A new network will be used to derive the new network, and then in both cases ZF, which is equal to 0, phase A and phase B is short circuited directly. In absence of ZF, the fault current flow will be higher. Thank you, that's all from me.